Okay, I'm trying out a new program today, so bear with me as I try to iron out all the kinks. But today we're looking at continuity and one-sided limits. Continuity just means we're looking at a function that's continuous. And it's about like you would expect it to be. A function is continuous, that is, it doesn't end. It keeps on going. It doesn't have any breaks in it. It doesn't have any holes in it. Okay? So a function is continuous at a certain point C, any point C, when these three conditions are met. F of C is defined, so the y value is defined at that point, at that x value of C. The limit, as x is approaching C, of the function exists. We talked about limits that exist and don't exist before. And the limit, as x approaches C, of that function is equal to the value of the function. So both 1 and 2 together for this third part. And what might that look like? Well, let's say we've got a function here. And oftentimes when we're talking about continuity and whether a function is continuous, we're looking on a certain interval. So let's say we just have some function here. Don't even know what. But we're looking on this interval here. We're looking at, say, between A and B. Sorry. Well, that's not doing what I wanted it to do. Between A and B. So here's our x value A, here's our x value B. So if I just want to limit, not a limit in this case, but just look at the scope, at the function in between here and here. In between these two x values. Okay, so any point C in between A and B, this function here, let me turn this pointer on. There we go. Anywhere between A and B, here the function at A and here the function at B. Anywhere in between here, the function is continuous. It doesn't end because of these three things. F of C is defined. Any value of C in between is going to be defined. It has a y value. The limit is going to exist in there. And whatever the limit is, it's actually equal to that particular value. Now, when continuity, sometimes when a function is not defined, it might look something like this. Say I have a function that comes along here, and at some point it has a hole in it. It's not a very good hole, but at this point, this function is not continuous. Why is it not continuous? Well, if whatever this value of C is here, whatever the C value is there, well, this y value, f of C, is not defined. So f of C is undefined. If that's undefined, it's not continuous. That was one of the caveats. Another example where we have something discontinuous, not continuous, perhaps the limit doesn't exist. So maybe I've got a function that's coming along and it's going up to infinity. Okay, there's an asymptote here. This is a case where the limit, if I've got some asymptote here at C, then the limit as x approaches C of our function, we said, does not exist. And then the third option, well, let's just do this. The third option is maybe I've got a function here and it's coming along, and then at some point there's something there, and perhaps the value for that, the value for that is actually a point right here at that value of c. So in this case, the limit exists. If I were to come along here and look, well, the limit's my expected value here and my expected value here. So the limit does exist. I would expect it to be right there. The actual value of the function exists right here. But since those two values aren't equal, then we say this is not continuous. So this is where f of c does not equal the limit as x approaches c of the function. So these are the three ways that a function can be not continuous. So a function that's not continuous we say is discontinuous. And there's two types of discontinuities. They're either removable or non-removable. Now the removable discontinuity was kind of like we just looked at. If I've got some function coming along and there's an empty hole there, we call that removable because it's like that point has been removed. Even if, so it's not defined there, but if it's removable, it's like we could stick that point right back in there. Or like that other example that I just showed you, it might be some other point. The point might be defined, just not where we'd expect it to be as far as the limit's concerned. That's also considered a removable discontinuity. Now, whoops. We're going to erase that. That doesn't erase. Okay. A non-removable discontinuity might be if I have a piecewise function. So I may have some sort of function that's coming along, and one piece comes along like this, and it stops right here, and then the next piece picks up and at that point and goes on up here. Well, this is considered a non-removable discontinuity because we don't know exactly where it's. We do know it's discontinuous at this point C, whatever this is, but we don't know exactly what to expect because we've got on one side here we would expect the limit to be right here, and on the other side it to be right here. So if we've got different limits on both sides, and we're getting to that in a minute, we don't know where it's supposed to be. So this is considered non-removable. Also, if we have a limit going to infinity, if we have something shooting up into infinity or down to negative infinity, we would consider those non-removable discontinuities also. Now we're going to talk about one-sided limits. Okay, now when we talk about one-sided limits, we're talking about one side or the other, either from the left or from the right at a given point. So we've talked about limits before. If I'm looking for, say, the limit as x approaches 2, okay, if I want to find the limit of some function, we have a little notation here, and if we put a little minus sign above it, that doesn't mean it's negative like that. This is saying this is the limit as x approaches 2 from the left of the function. Okay, so what that might look like if I've got some function here, I don't even know what, it doesn't matter, but I've got, okay, if I'm looking at the limit as x is approaching 2 from the left, that means I'm going to be traveling along the function this way, and I'm approaching it from the left-hand side of 2, and then I'll stop right there, and whatever that happens to be. So this is coming from the left, like that. I'm heading towards 2 from the left. And you can probably imagine, just want to move this up a little bit. Okay, you can probably guess that if I'm looking at a limit from the right, well, the limit, let's say I'm looking at x approaches 2 from the right, up a little plus sign. coming from the right of f of x. So if I'm looking at the same function here, well, if I'm approaching it from the right this way, I'm going to be coming along the function. I'm going to follow it along wherever it is, and then I'm coming from the right-hand side of it and hit right there. Coming from the right. Okay, so we've got limits coming from the left and limits coming from the right. Now, we say that a limit exists if these two things meet. That is, they equal the same value. So a limit exists it's hard to read, I'm sorry, if the limit as x is approaching some value from the left is the same as the limit of that x value approaching the same value from the right. So in this case, this limit would exist in this example here. Because as you see, as I'm coming from the left, I expect it to be right here. And as I come from the right, I expect it to be right there also. I expect it to be the same value. Right in here. So this limit exists because it's the same from the left and the right. One more point. This is the intermediate value theorem. Now this is a very important topic. You'll see this on the AP exam for sure, as far as you need to know how to use it and interpret it for both the free response and the multiple choice part. But here's what the intermediate value theorem says, and then we'll discuss it. If f is continuous on the closed interval from a to b, so this is a function that's continuous, and f of a does not equal f of b, and k is a number between f of a and f of b, then there exists at least one number c in the interval a to b, such that f of c equals k. Now, what in the world does this mean? Well, let's break it down. So we're looking at a continuous function, just as we have been. So this is some sort of function here that's continuous. Okay? On some closed interval. So we're on some interval here from, say, a to maybe out here at b. Okay? And it says f of a is not equal to f of b. So f of a is going to be about right here. F of a there. F of b is going to follow up to about right here or so. So f of b is maybe right here somewhere. Okay. Oof. There's f of b. And k is a number between f of a and f of b. So we know that k is somewhere in between here. Somewhere in here is k. Okay? So we've got some function between a and b here on the x. We've got their y values. K is some other y value in between those two. So as long as this is a continuous function, then there has to be, at some point, a number in here, in between a and b, to where when I plug it into the function, I get this value of k, whatever it is. And in this case, well, if I'm just looking at it graphically, I would follow it over, maybe over to about here. So there's some number in between a and b that give us this value of c. Well, this is a very rough sketch. This isn't anything exact at all, but this is what we call an existence theorem. Okay? We don't know what that c value is. We could probably find it given a certain function, but and there's examples in your book you can look at of all this stuff. But this just lets us know that there somewhere in between there it exists. Okay? We looked at something similar to this in Algebra 2 when we were looking for zeros of the function. Remember zeros of a function like of a parabola or a cubic function, some sort of polynomial? Okay, if we plugged in a value and got a negative, and then we plugged in another value and got a positive, say we plugged in, I don't know, something, say here, maybe this is the point 1, negative 3, and maybe I plug in another point over here, let's say maybe 4, and we get positive 3. Well, we've got a negative 3 and a positive 3. So we know if this is continuous, at some point it had to cross the axis. It had to equal 0. We had to have a 0 somewhere between 1 and 4. And we could find that. Anyway, this is, like I say, this is an important topic. We'll be covering it more later. It's your intermediate value theorem. There's examples of this stuff you can look at in your book, page 70 to about page 78 or so. And your assignment's going to be on page 79, 1 through 21 odd, 27 to 51 every other odd, and then 61, 63, 95, and 99 to 102. Give that a try, and we'll see you in class.